Sotiris. Thank you very much, Sotiris, for kindly inviting me to give this seminar. So the exact title is Riemann-Hilbert Problems and Integrable Equations. And actually, this is something that we did together with Alexander Stepanov. Okay. Как он, чтобы что-то...
Скорее всего, стрелками на клавиатуре.
Хорошо, понял. This is a list of several papers on which this talk is based. The most important one is the first one, which was published last year in Symmetry, which is rather long, but anyway, also the material there was a bit too much, maybe. The other all the papers of mine, and this monograph published in Springer, and some all the review papers that I did some time ago. So first, I will outline the standard approach to the inverse scattering methods. And then I will tell you how it is possible to reorder the steps, so to say, and get maybe a little bit better results. So the standard approach starts with the Lax representation. That is, we have a Lax pair, L and M, which are ordinary differential operators, as shown here, which depend on the spectral parameter lambda. Typically, in the standard approach, the Lax operator L is linear in lambda, while the second operator may be polynomial of higher powers in lambda. In this case, I will demonstrate the standard approach on the simplest non-trivial equation, the so-called nonlinear Schrödinger equation. The integrability of this equation was discovered more than 50 years ago by Zakharov and Chabat. And this is the nonlinear Schrödinger equation 1. So this is the first step is to demonstrate that taking the commutator of L with M, all positive powers of lambda disappear, and the lambda independent term actually vanishes if and only if the function Q1 satisfies the nonlinear Schrödinger equation. Now, how to solve this equation using the inverse scattering method? First, we have to solve the direct scattering problem for the Lax operator L. And this means that we have to construct the Yost solutions, which are determined by the asymptotics for x going to plus infinity, this is psi, and for x going to minus infinity, this is phi. The ratio of these Yost solutions determines the scattering matrix, T, capital T of T and lambda. The direct scattering problem means that we, starting from the potential Q of the Lax operator, have to determine the scattering matrix. And it follows from the compatibility condition on the Lax operators that the scattering matrix satisfies this simple linear equation with respect to time. So the time derivative of the scattering matrix is equal to lambda squared commutator sigma 3 with T of T and lambda. Okay, this is actually a rather well-known problem. It's been solved for a large class of operators, and it reduces actually to a set of linear integral equations. The third step is the construction of the fundamental analytic solutions. Now we want to solve the inverse scattering problem, actually. Constructing the fundamental analytic solutions, chi plus and chi minus, in this case, this is not difficult. These two fundamental analytic solutions, one of them analytic in the upper half plane, the other analytic in the lower half plane, and they are related on the real axis by this Soink function G0 of T and lambda. G0 of T and lambda is expressed in terms of the matrix elements of the scattering matrix. The last step is to solve the inverse scattering problem for L using the Riemann-Hilbert problem. This relation here can be interpreted as a Riemann-Hilbert problem with canonical normalization. And actually, to have canonical normalization, we have to introduce psi plus and psi minus, which are related to chi plus and chi minus by elementary exponential factors. In this situation, the Soink function satisfies these two simple linear equations, one with respect to x and the second with respect to time. And finally, we have canonical normalization, namely the limits of psi plus and psi minus for lambda going to infinity equals the unit matrix. Okay, so in what follows, we can have also singular points of the Riemann-Hilbert problem, and they are actually the eigenvalues of the Lax, or discrete eigenvalues of the Lax operator. And depending on what kind of reductions we have imposed on the Lax pair, we can have them in pairs or in quadruplets. Here is the situation. For the nonlinear Schrödinger, we can have only such complex conjugated pairs of eigenvalues. And if we put additional reduction, for example, that Q1, the function Q1 is real, then we can have this more complicated situation. The eigenvalues that are in pairs are purely imaginary, and the other more general eigenvalues are in quadruplets. This happens for the Sine-Gordon equation, for example. These symmetries that I demonstrated on the discrete eigenvalues are actually due to Mikhailov reduction groups. And Mikhailov reduction groups can can influence also the contour of the Riemann-Hilbert problem. In the previous picture, the contour was the real axis, and this was the continuous spectrum of the Lax operator. But we will have more general situations when the contours will be different, and then they must be, of course, invariant with the Mikhailov reduction group. Such more general situation may appear if we consider a situation when both operators depend polynomially on lambda with different highest powers of lambda, like that. And I will start with the typical involutions of the Lux representation, which in Mikhailov form are written like that. We act with some external with some automorphism of the Lie algebra of finite order. And for example, here this is the automorphism C1 applied to U Hermitian conjugates. And we act simultaneously also on the spectral parameter. And in this case, lambda will go into lambda complex conjugate. And we must get, again, the same U of lambda, which is determined here. And similarly for V. So we can have several types of involutions. So we choose one of them. We may have also more complicated choices for the Mikhailov reduction group. And when we apply Mikhailov reduction group, not only the contour, but also the discrete eigenvalues or the singularity points of the Riemann-Hilbert problem must be invariant with respect to it. So what are the possible choices for Mikhailov reductions? Well, since Mikhailov group must be a subgroup of the conformal group on the acting on the on the spectral parameter, we can have these choices for Mikhailov groups. ZH, diedral H, and the plateau solid groups, tetraedra, octaedra, and icosaedra. And if we apply any of these groups, then of course the Lux representation, which takes this specific form, must be invariant with respect to the Mikhailov reduction group. I demonstrated already that we may have such involutions on the U and V, and that means that, of course, this symmetry transfers to the Riemann-Hilbert problem, and the solution of this Riemann-Hilbert problem must also satisfy Mikhailov reduction group.
So, Volodya, since you have only 2x2 matrices, I think, yeah.
No.
Okay,
Don't
sure.
worry.
Okay.
This is just for the demonstrational case.
Okay.
Otherwise, in the future, we will have
only the header
U and E related to any simple Lie algebra, and the symmetries and everything will be applied on them.
Thank you.
And the final step is that we may use, after having the Riemann-Hilbert problem, we can use Zakharov-Shabat dressing method, so we can derive the soliton solutions. And then we can analyze also their interactions. But in this talk, I will not have the time to speak about the interactions. Okay. Before to outline my idea, I'll need also some additional tools to remind you. And for example, if we consider multi-component nonlinear Schrödinger equations, then we have to deal with symmetric spaces. This was discovered many years ago by Fordy and Coolidge in their pioneer paper in communications. So what does it mean that we have to use symmetric spaces? Let us choose a simple Lie group, G, and let its simple Lie algebra be small g. Then the symmetric space is determined by Cartan involution. Roughly speaking, instead of having sigma 3 that was in the first Lax representation, we have to deal now with J, which is an element of the Cartan subalgebra and which defines the Cartan involution, which is applied on G. Effectively, G is effectively G is split into a subalgebra G0 and additional linear space G1. And this splitting is actually a grading of the Lie algebra, which is such that if capital X1 and capital X2 belong to G0 and capital Y1, Y2 belong to G1, then the commutation relations here are such that X1 and X2 belong to G0, X1 and Y1 belong to G1, and finally, Y1 and Y2 belong to G0. For those who know a bit better simple Lie groups, I'll say that the root system of the algebra is the root system is delta plus delta minus. And now delta plus, the positive roots, are split into a direct sum of two subsets of roots, delta 0 plus and delta 1 plus. Delta 0 plus are the roots for which alpha on J is equal to 0. And actually, these are the roots corresponding to the block diagonal part of the corresponding elements. Delta 1 plus is the set of roots that have non-zero effect on J. Beta of J equals some constant B, which is positive and which may be equal either 1 or 2, depending on the choice of the algebra. Effectively, what happens is the following. If we take the typical representation of the Lie algebra, then J may be represented by block matrix sigma 3. G0 will be the block diagonal part of the elements of the algebra, and G1 will be the block of diagonal elements in that algebra. So typically this is enough to deal with multi-component NLS equations. Below, we will mention at some points orthogonal and symplectic algebras. And since we want that our Cartan subalgebras are diagonal matrices, we will use slightly different but equivalent definition for the orthogonal matrices and for the symplectic matrices. You see, U and V must be elements of the orthogonal or symplectic matrix, symplectic algebra. And here we have changed the definition slightly by this capital SA and capital S0 or capital S1. Capital S1 is for the symplectic Lie algebras, and capital S1 is given by this element. E with some indices, JK, means that this is a matrix that has only one non-vanishing element at position J and K. Okay, so in this case, this is a skew diagonal matrix, S1, and with S1, S1 prime. And the important thing is that S1 squared, S1 and S1 prime have non-vanishing elements which are only plus or minus 1, and the square of capital S1 must be minus 1. This is for the symplectic algebras. For the orthogonal algebras of odd dimensions, we must have S0 this is even dimension, sorry. Orthogonal matrices of even dimension. We have this form of the capital S0, and S0 squared must be equal to +1. This is the basic difference between the symplectic and orthogonal algebras. Okay. Now, we have to give a better explanation of what is Riemann-Hilbert problem and how Mikhailov group acts on it. So, Riemann-Hilbert problem, in the simplest non-trivial case, so to say here, is that we have two regions of analyticity. One is plus, the other is minus. We'll see what possibilities could be there. And psi plus equals to psi minus with multiplied by the Soink function capital G. As I mentioned before, capital G must satisfy some simple linear equations with respect to x and time. And here is just an example of these equations. N1 and N2 must be integers, typically 2 or larger than 2. And in addition, we have this canonical normalization. This canonical normalization is important because it guarantees that if we consider a reflection, if we consider regular solutions for the Riemann-Hilbert problem, then this regular solution is unique. That's why we need this canonical normalization. I mentioned already that the contour gamma of the Riemann-Hilbert problem must be invariant on the Mikhailov group action. And so we will also study more general Lax pairs, which are polynomial of higher orders in lambda. For example, U, the L operator, U now will be quadratic polynomial in lambda, and V will be a polynomial of 4. Note that these two polynomials must be taking values in the symmetric space, and because we are dealing with multi-component NLS equations, we have here J and lambda to power 4, J again. J is related directly to the Cartan involution. And in this case, we are looking now at the left picture here. In this case, the contour of the Lax operator of the Riemann-Hilbert problem will be the union of the real and imaginary axes. The region plus, so to say, which was mentioned above, is the first and the third quadrants, where the imaginary part of lambda squared is positive. The region minus is the second and the fourth quadrants. And you see that here we have actually two involutions. One of them is taking lambda to minus lambda, sorry, lambda to minus lambda. And the other one is taking lambda to minus lambda complex conjugate, and lambda to lambda complex conjugate. Okay, so you see that here we have discrete eigenvalues, which are in forming rectangulars. What we have here on the second picture is the possibility to add one more involution to the Riemann-Hilbert problem. And this involution is taking lambda. Where is lambda? It's taking lambda into 1 over lambda, or minus lambda into 1 over minus lambda. And now, as a result of this additional involution, the contour of the Riemann-Hilbert problem becomes more complicated. Now, besides the two axes, imaginary and linear and real, we have the unit circle. And now we have sets of eigenvalues that come in 8, because they contain not only lambda, 1 over lambda, but also minus lambda, minus 1 over lambda, and their complex conjugates. So I show this picture just to give you an idea how more complicated Mikhailov group could affect the Riemann-Hilbert problem. And it is really very important that from the very beginning we make the Riemann-Hilbert problem compatible with Mikhailov reduction group. After that, we can analyze what happens with the singularities and things like that. Okay. Here is another example of a Riemann-Hilbert problem. And now we have not set of several involutions, but we have a situation when we have ZH reduction group. H here equals to 12, and you see that here we have 12 straight lines which close equal angles to 30 degrees and which split the complex lambda plane into 24 sectors. One can define a fundamental analytic solutions in each of these sectors. And now the Riemann-Hilbert problem is written in a little bit different way. It is not just one relation, xi plus equals something to equals xi minus to something, but now it is xi nu plus 1 equals xi nu multiplied by the Soing function g nu. And of course, all these relations must be invariant under Mikhailov reduction group, which in fact acts like that. It takes L0 and takes it to L2. So the Coxeter number is 12, and it takes L0 into L2, then to L4, etc., and it takes L1 into L3, then L5, etc. And effectively, the independent parts of the relations that determine this Riemann-Hilbert problem are the data on the two rays, L0 and L1. All the rest are obtained from these two rays acting with Mikhailov reduction group. Okay, here we are not on a symmetric space. Symmetric space does not allow such reduction. But J consists of, is a diagonal matrix that consists of the powers of omega, which is root of order H of 1. Actually, this result, in fact, was obtained by Mikhailov back in 1980 when he discovered his reduction group, and when he demonstrated the two-dimensional total field theories. Okay. Let me now try to formulate my alternative approach. So let us start with canonically normalized Riemann-Hilbert problem related to a symmetric or homogeneous space with predefined contour gamma invariant with respect to Mikhailov reduction group. So I'll keep here the simplest non-trivial case, and you will easily guess when you have different Mikhailov group how to reformulate the problem and do all the rest. So here, as I mentioned a bit before, I will stick back again to multi-component nonlinear Schrödinger type equations. So xi plus equals xi minus times g, and g satisfies these two simple linear equations with respect to x and time. And then, of course, we have canonical normalization. So the second step is to introduce parametrization of the Riemann-Hilbert problem. And we introduce it using their asymptotic expansion. Psi plus and psi minus have the same asymptotic expansion, and we formulate it as exponential of this Q twiddle or whatever, which is a series, depends on xt, and which is a series over the inverse powers of lambda. Why inverse powers? Because when you take the limit of this Q for lambda going to infinity, you get 0, and therefore the canonical normalization is satisfied. Okay? And now we can pick up the coefficients that enter into this parametrization. I do not have a complete theory of how this Q twiddle can be reduced, but at least for the examples that will follow, we can assume that all coefficients in the expansions of Q are off diagonal, block off diagonal. That is, belong to the subspace G1. Now we have, of course, the structure of symmetric space, and we have this grading. In addition, I have assumed also that the function Q twiddle is changes sign when lambda changes sign. So we have here only odd powers of lambda, odd negative powers of lambda. So this is the way it is formulated. In addition, I assume, of course, the typical Mikhailov involution, that is P1 and Q1 are Hermitian conjugated to each other. Minus sign is important also here. Okay. Okay, we have parametrization of the Riemann-Hilbert problem, which will be useful to construct the Lux pair. Now, how to introduce the Lux pair, starting from Riemann-Hilbert problem? To this end, we use the ideas of Gelfand and Dickey. Many years ago, in some occasion, they stated that the following parametrization of the Lux pair could be very useful and convenient. I will not explain in detail their ideas and what they did, but I will just formulate the result for our situation. U of xt and lambda This is evaluated like this. We take lambda squared psi j psi inverse. Psi is the solution of the Riemann-Hilbert problem. Psi j psi inverse is an element of the Lie algebra. This is a similarity transformation on the Lie algebra element j. And then, so we multiply this element by lambda squared, and then we take only the polynomial part of this expression, okay? For the M operator, we follow again Gelfand-Dickey and take now lambda to power 4 psi j psi inverse, and again take the polynomial part only. So, and here we remind that psi plus minus were the fundamental analytic solutions of the Lax operator, L, multiplied by some standard exponentials here. Now, it seems very complicated. We have psi as this exponential of infinite series, and so to calculate these expressions, we get also presumably an infinite series. That's true. But at the same time, we have this great idea that we must take only the polynomial parts of these expressions. And in addition, I'll remind you that here the upper hat means inverse, actually. So psi plus j, psi plus inverse can be expressed using the standard formulae from Lie algebras as j, this is the first term because, okay, plus 1 over k factorial at of q twiddle to power k over j. What it means? It means that at q, acting on any element of the Lie algebra, is just taking the commutator with it. At squared q means that we must take double commutator, etc. Okay. So this is, of course, an infinite series, but since we need only the few first terms here, it is not so difficult to calculate them explicitly. I have put here the explicit expressions for the case when Q1, Q2, etc. are generic matrices. And you see that, okay, V4 seems rather complicated indeed. At the same time, I have imposed two reductions on these Qs. First of all, Q2 equal Q4 equals 0. And second, these were block of diagonal matrices. So when you try to calculate these things, it comes out to be not so complicated. For example, U1 and V1 are equal, and they are this associative Hermitian matrix. U2 and V2 are equal to just 1/2 Q1 with that Q, and it is block diagonal Hermitian matrix. V3, this is the expression for V3, off diagonal. And finally, V4, which is again a block diagonal. Okay, it doesn't come out to be so terrible, huh? Then, after we have the Lax matrices, the Lax operators, we can write down the compatibility condition, which takes this form. And when we replace here the coefficients of capital V and capital U, we obtained that the first highest terms, you see, we have Lux pair, which is with lambda squared and lambda fourth. Sorry, where was it? Okay, here we have lambda squared, here we have lambda to 4. So when we try to calculate the commutator, we get the highest power lambda 6. However, it is vanishing, and you can easily see that all the other powers until lambda cube are vanishing identically. Lambda 6, lambda 5, lambda 4 vanish identically. And what we have is equations that must be satisfied for the compatibility condition is that lambda cube provides us that actually V3, the third element in V, must be expressed with the x derivative of Q1, actually. Actually, Q is a little bit different from Q1. Where was it? Okay. Q is actually J multiplied by Q1. So this is J multiplied by Q1, and this provides V3. Lambda squared. Lambda squared, we have this condition, and from here we can define V4. V4 of actually J with V4 commutes because both are block diagonal. J is sigma 3 and V4 is block diagonal. So from here we define V3. Lambda to power 1 gives the equations, and lambda to power 0 gives another equation. So our result is that V3 is actually Q1x, I over 2 by capital Q1x. Q3, so V3 was expressed in Q3 small, I expressed in this Q1 again. V4 was this fact, and I don't have the time to explain all the details, but this is the result for the corresponding multi-component nonlinear Schrödinger equations. You see, we have quadratic pencils for both for L, and therefore we have nonlinear Schrödinger equations with derivatives and higher powers, fifth power here in the nonlinearities. And so these are the two equations. One of them is obtained by taking the Hermitian conjugated of the other. What we had also were some terms which corresponded to lambda independent terms in the compatibility condition, but I checked that these additional terms provide equations which are consequences of this equation 7. So I do not put them here. Okay, so thus, starting from Riemann-Hilbert problem, and we constructed Lux pair, and we obtained the corresponding nonlinear equations of multi-component NLS time. Next, the last step here is, since we have Riemann-Hilbert problem, we can use the Harushebad dressing and derive the soliton solutions. And of course, we have to take into account all the symmetries in the Riemann-Hilbert problem. So, since we have canonical representation, canonical normalization, we, for lambda going to infinity, we have xi plus and xi minus that tend to 1. And obviously, we can pick up xi plus and xi minus equal to 1 as the simplest possible regular solution. Obviously, this is unique due to the canonical normalization. And now we will apply Zakharov-Shebat dressing method to calculate soliton solutions of our multi-component nonlinear Schrödinger equations. How? We define psi naught plus and minus. These were just the standard exponentials, as you remember. And then we will construct chi1 plus and minus, which is obtained from chi0 using the dressing factor of Zakharov and Shebat. So I will demonstrate to you that in this way, how in this way you can obtain the one soliton solution of this. And actually the scheme is such that it can be repeated many times. So in general, you can always calculate the multi-component, the multi-soliton solutions. Excuse me. How to do the dressing? Just a moment. Okay. How to do the dressing? How to calculate this dressing factor? Before to explain this, I'll mention here, we will treat two situations. The first one is if we have C1 symmetric space, which is related to the algebra SP6, or if we have a D3 type symmetric space related to SO8. In this case, the matrices Q1 or Q1 soliton solutions will be actually 3 by 3 matrices in the case of C1, like that. Or it will be 4 by 4 matrix for the orthogonal 8, like this one. In both cases, we will have 6 components. And the corresponding equation that must be satisfied is this one. We took just one of the previous equations, which is enough. So, in this case, the dressing factors and subject to 3 involutions. One of them was lambda going to minus lambda. Another one was lambda going to lambda complex conjugate. And the third involution was that actually they belong to a symplectic orthogonal algebra. And therefore, if we write down the dressing factor like that, then the inverse powers of this dressing factor must be obtained by acting with these capital S matrices that I introduced in the beginning and transposition. Okay? The inverse of U is obtained by taking the transposition of this U and acting with S0 or S1 minus 1 on both sides. So in this case, we have 4 singularities in the dressing factor. For U, these are the points lambda 1 minus and minus lambda 1 minus, at lambda 1 plus and minus lambda 1 plus. And when we calculate the inverse of this, well, okay, the singularities now come again into the same point, lambda 1 plus, minus lambda 1 plus, lambda 1 minus, minus lambda 1 minus. How to calculate now these singularities? Okay, we have this explicit form of the singularities. This is explicitly the lambda dependence. not only the singular points, but we have also here lambda. And we have here some residues. The structure of these residues is that they are of rank 1. Actually, capital N1 is a column with the size of the corresponding to the matrix Q1. M1 is a row, okay? So we have column multiplied by a row with the corresponding size. And here we have the same residue, but multiplied by J and J inverse on both sides. And then we have other residues, M1 and small n1, which are multiplied here by the typical matrices S1 or S0 that determine the structure of the algebra. And one more residue of that form. Okay. So how to calculate them? Of course, the tool that we will use is the fact that this dressing factor relates two solutions of the same Lux operator. Corresponding, one of them is the naked solution, chi0, the other one is chi1, corresponding to the one soliton case. And this means that you must satisfy this ordinary differential equation. And also U inverse must satisfy similar equation. So here U2 and U1 correspond to the one soliton solution of the Lux operator. U20, U10 are actually vanishing because we start from a trivial regular solution. What next? We must remember that these equations must be fulfilled identically with respect to lambda. This is very important, and this is in the idea of the Dressing-Zakharov-Shabat method. How to ensure that this U can be such solution to equation 8? Well, you will satisfy this equation if and only if all the residues at the singular points vanish. Okay? You see, U is a fraction linear in lambda. Rather complicated, but fraction linear. So if all the poles of the solution, all the residues at the poles that is this solution vanish, then everything will be okay. The equation will be fulfilled identically with respect to lambda. And now I'll, if you put here now U, this long expression, you put it there, and you calculate the residue at lambda 1 minus. What it means, you multiply by lambda minus lambda 1 minus and take the limit when lambda goes to lambda 1 minus. Well, this is not very difficult procedure. It provides us with this equation for the first residue, capital N1 by small m1. This is a column, and this is a row. And then we have this U2 plus lambda 1. We have applied, taken the limit lambda to lambda 1 minus. So here stays the Lux operator potential evaluated at lambda 1 minus and multiplies this residue minus the same residue multiplied by this naked, so to say, value of the potential for lambda. Actually, as I mentioned, U2 0, U1 0 are vanishing. So it remains only the last term here. From the equation for U inverse, we obtain similarly, no, from the same equation, we obtain also the equation for the residue small n1 capital M1, which is expressed in lambda 1 plus here. We take the residue at lambda 1 plus, and so we obtain these relations. And now we have to solve these equations. How to solve them? Well, you see, when we take the derivative of the first term, we differentiate first capital N1, and then it is multiplied by small m1 on the right. And so, and then we have to take these terms. We get the x derivative of capital N1 plus u2 minus lambda 1 minus u1 minus lambda 1 minus squared j over n1 again. This is maybe taken in front of the bracket, and that bracket will be multiplied on the right by small m1. Similarly, the derivative of small m1 will be an expression proportional to capital N1, and inside there will be some simpler equation for M1. Actually, it will give us that M1 will be a simple exponential with lambda 1 minus, as it is shown here. So it is not so complicated. The solution is not difficult because we have taken residues of rank 1. And actually, in order that our solution for the dressing factor up there is satisfied identically with respect to lambda, we need that capital N1 be the one soliton solution evaluated at lambda 1 minus, multiplying some constant column. M1 must be M1 0 constant row multiplied by this exponential. This we know. Chi1 minus we do not know. Capital M1 similarly must be some constant row multiplied by Chi1 inverse evaluated at lambda 1 plus. This we do not know. But we know small n1, which is this simple exponential at lambda 1 plus acting on the constant n1 0. And so what else must we do? Okay, we made the first step to calculating the one soliton solution. We denote here lambda 1 plus and lambda 1 minus, express them by the real and the imaginary part of lambda 1 plus. And then we remember that actually U and U inverse must belong to the corresponding group, and that U and U inverse multiplied must give us the unit matrix identically with respect to lambda. Again, identically with respect to lambda. What does it mean? Well, we have to multiply U and U inverse and calculate the residues and put them all to 0. Excuse me, please. This is also some calculation. First, there are residues of second order that must vanish. And these residues of second order vanish if and only if we insert these conditions on the polarization vectors M1, and this is M1 0 by here we have the matrix S0 related to the algebra and J, and so M1 0 left, S1 J, M1 0 must vanish. And finally, there are some technical calculations here. I do not have time for that. But actually, if you pick up the paper in symmetry, you will find them and you will see it's not so difficult. So what we get is the following. Actually, we get this relation between the small m1 and n1 with the capital one, m1 capital and n1 capital. I remind, these were some simple exponential factors that were given up here. Capital M1 and capital N1 were something that we do not know and that we want to calculate. So, the expressions for x1 and x2, y1, y2 are given here explicitly in terms of the scalar products of these polarization vectors, small m1, small n1. You see? And finally, what we obtain is a linear system of equations which we must solve in order to define M1 and N1 in terms of small m1 and small n1. So we need to evaluate the inverse of this matrix. This is block matrix, and well, it's not so well, there is some difficulties here, but not very big ones. You need to know some algebra, and that's all. So the inverse of that matrix is the ratio of these functions G2 and W2. Here is this ratio written down in terms again with small m1 and small n1, and it must must multiply this block matrix, which we have again expressed in small m and small n. Okay? So finally, our answer is the following. Capital M1 is this function that we mentioned above, some factor multiplying M1 and another factor multiplying Jn1. Capital N1 is the same function, some factor multiplying small n1 and another factor multiplying small m1. So now we have expressed the one soliton polarization vectors by the functions that we know. So these are some rational functions of exponentials. This is the result for the one soliton solution. And now we have to calculate the potentials. In order to calculate the potentials, we take these equations that are satisfied by small u and small u inverse. We take the limits for lambda going to infinity. This is typical for the Zakharov-Shebat dressing method. And from here, we derive the final results. So the one soliton expression for u1 is twice I nu 1, this commutator J with capital R1. Capital R1 is put here, and now we have to replace the M1 and N1 by these expressions. You see the expressions become rather long, but well, nothing is simple in this on this level, so to say. U2 one soliton is twice I nu 1, capital commutator J with R2, and R2 is also put down here. We have explicit form for the one solitons. It takes a little bit of courage to calculate the two soliton solution. I have not done it yet. I know it's rather technical, complicated, but I'm sure it's possible. So the final answers. U1 with one soliton is this off-diagonal matrix, and U2 one soliton is this block diagonal matrix, and Q1 soliton is this expression, Q2 soliton is this one, capital N, capital M, we already know. Okay, you could continue, of course, and probably I also will continue some later time. Define the resolvent of the Lax operator and use it to analyze the spectral properties, etc. But okay, sometime later this will be done. So for the case of SO8, remember Q1 was 4 by 4 matrix. And for SP4, it was 3 by 3 matrix. So, of course, this capital U1 and capital U2 already have the necessary dimension corresponding to the symplectic and orthogonal cases. Okay, so here we took some time to plot the one soliton solution. And here you can see, here I have put the first three, I think the first three for C1 type, the first three coefficients in the potential, and these are the second three potentials. And I put them on different graphics because you see the size here is up to 12 or something, while here the maximum reaches 160. So if I put those three functions also on top of this, you will see them, you won't see them at all. For SO8 multi-component NLS, we found something uncommon, so to say. This is one soliton solution, and you see that typically all its components have two maxima instead of just one, and have a minima in the here. We cannot have good explanation why that may happen. What might be the physical effects of this? We still don't know, but anyway, we just present the fact. This is another plot for another values of the eigenvalue, mu1 equal 2, mu1 equal 1. Again, we have the same type of situation. Okay. How much time do I have?
Vladimir, normally the time is over, but if you have some important
Okay. For
5 minutes.
Okay. For the Lax pairs related to symmetric spaces, there were no difficulties to calculate the compatibility condition of the two Lax operators. However, if we consider Lax pairs related to homogeneous spaces, the situations become different. And here I have put the compatibility condition when we have cubic P equals 3, and in M we have also lambda to power 3. So we have two Lax operators, but with two different elements, J and K, from the Cartan subalgebra. This is homogeneous spaces. There is J is not matrix sigma 3. And we calculate again U and V using Gelfand-Dickey approach. We calculate the commutation, the compatibility condition here. It must be satisfied to any power of lambda. What happens here is a little bit different than for the MNLS case. To power lambda to power 6, J and K are diagonal, so this is trivial. To lambda to power 5, this is not very difficult linear equation, so it can be solved as it is shown here. But lambda to power 4 and lambda to power 3, you see this not very simple matrix relations. They must be satisfied identically. So the question is, how do we parameterize these matrices U1 prime, U2 prime, U3 prime, etc., so that these relations are identically satisfied? Well, we have been lucky. We get this parameter, we get the corresponding expressions for U1, U2, U3 using Gelfand-Dickey approach. So here I have put the first three terms in the parameterization of psi, and we have to calculate these polynomial parts of lambda cube psi j psi inverse, and here is what is the result. And the good result is that after all, the U1 prime, U2 prime, U3 prime satisfy these conditions, satisfy these equations identically indeed. So Gelfand parameterization of Riemann-Hilbert problem and Gelfand-Dickey formula allows us to obtain a whole new class of Lax operators, which allow fundamental analytic solutions, since they are obtained with Riemann-Hilbert problem, and that allow application of all the technique that was developed here. So there is a new class, so to say, of Lax operators that could be generating new hierarchies of integrable equations. Thank you very much.
Thank you.
Thank you very much.
However, we have some time for questions.
Yes.
Yes. Are there any questions? If not, Vladimir, you're interested in one soliton solution with two maximum. Are there any reason to hope that there are some interesting phase transition phenomenon for multi-soliton solutions?
First of all, I'm not sure. I'm not too good physicist, and it is not very easy, I would say, to define the physical effects of, say, SO8 multi-component NLS system. It may have. I don't know. It may have. But fortunately, I do not know and cannot say anything about this. It's a very interesting question, and it's not easy at all.
Thank you. Okay, if there are no other questions, the today's seminar is finished, and I'd like to thank you all and see you soon. Bye.
Thanks, Volodya.
Thank you very much.